Hello, welcome to Sigma Maths. This is the first video in a series covering the Exponentials and Logarithms content of the Maths A-Level. I will be referring to the Edexcel specification, but most of the content is very similar across all of the exam boards. This section of the A-Level appears in Chapter 14 of the Pearson Pure Mathematics Year 1 AS textbook. In this video, we will be taking a close look at 6.1 and 6.2, as you can see on the screen now. This covers the exponential graphs, base e, and the gradient function of e to the kx. The next video in this series will be going through a variety of practice questions on what we will be covering in this video. Okay, so if we start by having a look at the graph of y equals a to the x. Now we've got two cases to consider, very similar in shape, but with a very distinct difference. The specification mentions that we need to be aware of the difference in shape between a is greater than 1 and a is less than 1. Now, just to make sure we cover all of the options and we understand what we're working with here, we need to make sure we know why we are missing out the case of a equals 1. So if I just pop over here, the example of y equals 1 to the x, we can see why this isn't really something that we need to consider in the same family as a is greater than 1 and a is less than 1. If you think about changing the value of x for this particular function, if we had x as 0, 1, 2 and 3 for example, we would see that y would take the values of 1 to the 0, which is 1, 1 to the 1, 1 to the 2, 1 to the 3. They would all be 1s, be a very uninteresting graph, just a straight line through y equals 1, therefore not falling into the same category as the other exponential graphs. So we are strictly looking at less than 1 and greater than 1. So to begin with, we will take a is greater than 1. We'll take a particular example so we can really think about what's happening. It really is a very good idea to get to know these graphs, not just for the sake of sketching them in exams, but also so that when you're doing things like modelling, you have a good idea of what the equation in front of you actually does visually and over a long period of time. So when you think about like when x tends to infinity or time tends to infinity. So to start us off in our thinking, we're going to have a look at y equals 2 to the x. So this has base number 2. That's always the large number that the power is raised to. And we're going to put a few values of x in just to get us going. So I've got a table ready here. So we're going to put in 0, 1, 2 and 3 so we can see what happens to the function as we move along the positive x-axis. So we have 2 to the 0. We know that everything to the power of 0 equals 1. 2 to the 1 is just 2. 2 squared, which is 4. And 2 cubed, which is 8. And if we just think ahead, if we carried on doing this same process, we're seeing it is basically doubling every time, very much a geometric sequence. So 1, 2, 4, 8, 16, 32, 64. And we can see that for very small increments in x, we are getting very large in the values of y. If we just picture this, so do a very quick little sketch here. So we're starting on 0, 1, just here. Small values of x increasing results in large jumps in y. So we're having this kind of very getting steep very quickly section of the graph here. We're also going to make a note here that as x increases, we can see no matter what happens that y also increases. Okay, so it is an increasing function, certainly for x is greater than or equal to 0. We will see this is also the case for negative x in just a moment. Okay, so another table of values for us to investigate some negative values of x, going from negative 1 down to negative 4. So 2 to the negative 1, we know from our indices work that this means do the reciprocal of the base number, so it's a half. 2 to the negative 2, a quarter, negative 3 and 1/8. So we can see what's happening here. We can see the pattern. 1 over 16 if it carried on, 1 over 32, 1 over 64. And these numbers are getting very small very quickly. Okay, so if we picture it, on a quick sketch of an axis, we can see again, so we know that 0 is 1, and then we drop down to a half and then a quarter, so it's going to go kind of difficult to draw. It's going to keep getting closer and closer to the x-axis as we go down towards negative infinity, but it is never quite going to get there. We realize that every time we are halving, you can halve something as many times as you like, you are never going to make it disappear. So we're never quite going to touch. So when you do these sketches, you just make very sure that you are always getting closer and you never accidentally flick up again like this at the end. But also, you don't want to go down and touch the x-axis either. So you just got to practice that skill there. It's always good to get good at your sketching. Okay, so I'm just going to make some statements here using the tends to notation. So if we go back to positive x values, we can make the statement that as x tends to infinity, y also tends to infinity. And if you make a similar statement for the negatives, we can say as x tends to negative infinity, this time y tends to 0. So this is what we were just talking about here, where we get closer and closer to the y-axis but never touch. And this particular aspect of the graph is called an asymptote. Okay, there we go, asymptote. It's very important that you're aware of features like these for all the different graphs that you have to know for the A-level. You also need to make sure you label them on your sketches. Okay, so let's get rid of that and have a look at a graph that I have made in Desmos. If you're not already aware of Desmos, the graphing calculator, it's one that you can use online in your browser. I strongly suggest you have a little play around with it. It's very useful for getting a quick idea of what various functions look like. You can plot multiple graphs on one, and it really is just very simple and easy to use piece of software and free, so check it out. Okay, so I'm just going to add in my x and y labels. Should never have a graph without our axes labeled, so we know what's going on. So this is the graph of y equals 2 to the x, the one that we were just having a look at, drawn out very nicely for us. So we've got this very important point here. It's important because whenever we're asked to do sketches, we should always be labeling our intersections with both the axes. Now this graph in particular, graph of y equals a to the x, only has one intersection when it hasn't been transformed, and it will always go through 0 and 1. That will be because whatever number we put in place of a, if we raise it to the power of 0, we know that anything to the power of 0 is 1. So we're always going to have this intersection point here. On this side of the graph, we can just rewrite this as x tends to infinity, y tends to infinity, to remind ourselves that's what we're looking for this particular style of graph. Remember, this is the a is greater than 1 graph. And then over here, we can just remind ourselves that as x tends to negative infinity, y tends to 0. And yes, we're going to label this. The x-axis, really it's just the negative x-axis because the graph does not tend to the x-axis on the positive end. We're going to name this, remember what it was called? Asymptote. There we go, don't forget that P in there. And I mentioned earlier when I spoke about this that we need to label the asymptote, not just label it like I have here, but label it with the equation of the asymptote. Now this is a straight line going through y equals 0, so you just put in y equals 0. It's quite difficult to make an asymptote obvious on a graph where it's on the axis, but what you'll see a bit later on in the video when we look at transformations of this graph, we will find that there are particular transformations that will move the asymptote up or down, and we'll actually be able to draw it on as a dashed line onto our sketch, making sure we put our label next to it so it makes it a little bit more obvious. Okay, so we are hopefully fully understanding why this graph looks the way that it does. As we raise a number to higher and higher powers, it gets very large, so we have this tending to infinity. And as we raise it to negative powers, it is the same as doing the reciprocal or doing 1 over, and therefore we are getting very small very quickly. It's an interesting phenomenon of getting infinitely smaller but never reaching 0. Okay, so now that we've covered a is greater than 1 with the example of y equals 2 to the x, we are going to have a look at a is less than 1. So let me just open this up. here we go. So we're going to take the effectively the opposite example to the one we just took, y equals 2 to the x with y equals a half to the x. So this can be replaced with anything less than 1 in here, but I thought it would be nice to use the same reciprocal base number as the last example. So we're going to do the same thing here. Just going to stick our x values in so we can get a feel for what's going on. Before I start filling this out, just have a little think to yourself, well, how is this going to look the same and how is it going to look different to our last example? If our base numbers are half this time, should make a fairly simple change to what we see. Okay, so a half to the 0, put brackets around that there, that's going to give us a value of 1. Half to the power of 1, well, that's just going to be a half squared, a quarter, a half cubed, an eighth. And if we carried on, a 16th, 1/32th, etc. So this should be looking very familiar. This is the same as the second table that we did for the first example, so keep that in mind. Okay, I'm going to make a little statement about what's going on. As x tends to infinity, y is tending to 0 this time. So quick sketch whilst we're thinking about it. X, y starts on 1, going like that. Oh, much better. Do not touch, remember, do not come back up again. If you feel like you're going to have to touch or come back up again, just stop wherever you got to. Okay, now we have our second table going into the negatives. So thinking carefully about this, making sure we get our indices right. A half to the negative 1. Negative power means reciprocate. Reciprocal of a half is 1. So we get 2 to the 1, which is 2. Sorry, negative means reciprocal. Reciprocal of a half is 2. I think I just said reciprocal of a half is 1. It is indeed 2. Okay, a half to the negative 2. Again, reciprocate to get 2, square, 4. A half to the negative 3. The negative reciprocates to get 2, cube to get 8. And then the same here, 16. It carries on, 32, 64. It is literally like we have swapped these two tables around, all just because we did 1 over the base number, made it a number less than 1. So if we drew this as a sketch, we have got starting on here, and we're going up and getting steeper and steeper like we did with the positive values of x on the last one. So as x tends to negative infinity, y tends to infinity. Okay, let's have a look on a Desmos graph. See how good that looks. There we are. Okay, so it is just like we have flipped around. It's a reflection, in fact, seeing as we have 2.5 as our base numbers. This is just a reflection of y equals 2 to the x. A reflection in the y-axis. So we've got x and y labelled. Y equals a half to the power of x. Again, as I mentioned last time, important point, we are always going to have it 0, 1. That is if we haven't got a transformed version of this graph. If we've just got the standard y equals a to the x, whether it's greater than 1 or less than 1, we're always going to pass through this 0, 1. We've got over here, as x tends to negative infinity, y tends to infinity. And over here, as x tends to infinity, y tends to 0. Remember, we have important feature of this graph, the asymptote. Not the only graph that you have encountered that has this feature. You should have encountered the reciprocal graph at GCSE level, where you would have met asymptotes and the importance of labelling them, hopefully. So y equals 0 again, same asymptote as before. And there we have it. So the two graphs look very, very similar. They're just a reflection of each other in the y-axis. So you just need to keep an eye on the base number, see whether the base number is greater than 1 or smaller than 1 to determine which way around it's going to go. And if you forget, just have a little think about some of the x values. Do the y values get larger as x gets larger, or do they get smaller? And then you'll know which way around you are going. Okay, so now we're going to have a look at some transformations, and we're going to apply each of the standard transformations to our running example, y equals 2 to the x. Just a little reminder for ourselves of what the graph transformations are, and what it looks like when you apply them to this graph. So the first one we're going to look at, okay, so this isn't necessarily a standard transformation. This is very particular for the graph of y equals a to the x, but it was just to show you what's happening to the graph as we change the value of the base number. So the red graph that you can see in front of you, y equals 2 to the x, so we can see it goes through 0, 1, got the standard exponential shape. And then if we, I know I've just chosen integers here, but if we increase up from 2, so even if we went to 2.5 or we went to 3.7 or 10.2, you just look and see what happens. So obviously if our base number is larger, as we raise that number to higher and higher powers, we're going to increase more quickly. So you can see that the blue and the green graphs are higher earlier on than the red graphs. They're getting steeper quicker. The gap is getting larger and larger as they go. All the graphs still pass through 0, 1, because anything to the power of 0 always equals 1. And then if you just look on the other side, interestingly, they all swap positions. So on the positive x-axis, we've got the red is at the bottom, the red graph, y equals 2 to the x. But then as we go into the negative values, the red graph is now the highest value all the way along. And that's because the blue and the green ones are 3 to the x and 4 to the x. They're now to the negative powers, so they're like powers of a third and a quarter, and they get smaller a lot quicker than powers of a half. So even if you just think of the squared and the cubed, if you square and cube a half, you get a quarter and an eighth. If you square and cube a third, you get a ninth and a 27th. So you can see they're definitely getting significantly smaller. All three though, still having an asymptote of y equals 0, still always getting infinitely closer but never quite reaching there. But it is quite interesting the way that they cross over at this point, 0, 1. Okay, good. So first transformation of y equals a f of x. So I've written that in notation that you should recognize from both GCSE and earlier chapter of the A level. So we're just going to make a note of what this transformation is. Hopefully you're already thinking to yourself, well obviously that is a stretch in the y direction, and it is scale factor a. Okay, so when things happen outside the function, they are affecting the y values and they act in a way that you would expect them to act. It's important you remember that, because obviously when you're looking at transformations inside the function, it is the other way around. It's the opposite to what you'd expect, but we'll get to that in just a minute. So we've got the example we've been using so far, y equals 2 to the x in red. That's the one in the middle there. And then we've got an example of multiplying the whole function by 3. So note that is not the same. That is not equal to 6 to the x. I'm going to be very careful not to make that mistake, because that 3 is not part of that power of x there. So this is like having 3 times f of x, that transformation there. We can see that it has made the whole graph 3 times as far from the x-axis as the red graph. That's the whole idea of the stretch scale factor 3. Important things to notice: we are now going through 0, 3 rather than the 0, 1 that we would normally get. So as I said earlier, this point of intersection is always present on the exponential graphs, except when we have particular transformations that move it. So in this case it was stretched up, because you get 3 times 2 to the 0, which is 3 times 1, which is just 3. So we can see that's definitely going to be the case. Otherwise though, the graph looks exactly the same. When you are sketching, bear in mind, you do not have scales on your x and y axis. So it wouldn't necessarily look any different to if you sketched y equals 2 to the x. You would just label your intersection point differently. Still got the asymptote down here of y equals 0. And then we've got an example here of 0.2, which is a fifth, times the function of 2 to the x. So that's like having a fifth outside of the function here. So we'd expect it to bring it a fifth closer. And you can see here the green function is much closer to the x-axis than the red function was. The intersection point has gone through the same process and would now be 0, 0.2. Brought that much closer, and still has the same shape again, not as steep, grows slightly slower, but still same overall shape as I mentioned for the blue curve. So that's what these particular transformations look like. Now we're going to have a look at the same type of transformation but inside. So here we go. y equals f of a to the x, so we're inside the function. So again, this is a stretch because we are multiplying. It is in the x direction because it is inside the function. And then the most important bit, the scale factor, will be 1 over a. Okay, so if it was a 2 in here, then it would times all the x coordinates by a half. So it's more of a compression really, rather than a stretch with a scale factor less than 1. Okay, so again, red, y equals 2 to the x. And then we have multiplied by 3 inside the function for the blue. Now, because of the shape of this graph, if we were sketching y equals 2 to the 3x on its own, the shape wouldn't look all that different really from if we were just sketching y equals 2 to the x. It's obviously brought in closer to the y-axis because all the x coordinates have been divided by 3. But the shape's not going to look massively different. What we are noticing here though is that when we transform inside, because this point here has x coordinate 0, it does not change for any of these transformations, okay, because we are affecting x coordinates only here, and multiplying 0 by any number that you like doesn't change it. It still remains a 0, so we are fixing this intersection point for all these transformations. I've got an example here as well of a half times x, so I'm just going to mention here this is f of 3x, that's what that would look like. This would be f of a half x. This one actually stretches it out twice as far, so you can see the green one looks more stretched out than the red one. Again, if you were sketching it on its own, not with the original graph, the shape would be very much the same. Okay, you only really see the difference here when you sketch it with the original graph. Notice we've got the same thing as when we were changing the base earlier. So here the red function is higher than the green function because it is growing more quickly. But then when you go down into the negative x values, the green one is now on top and the red one is underneath. Okay, that's the nature of the negative powers and their reciprocal effect. Okay, next transformation, slightly easier one here. So plus a. So remember, this is you know what it is, translation. And we usually say by the vector, or by, and then we draw the vector. So this one does nothing to the x values because it's outside the function. It does what you would expect to the y values. So we're going up by a. So we just have a positive a in that part of the vector. So this is picking up the entire graph and shifting it upwards by a value of a. So again, red graph, y equals 2 to the x is on there. And then our blue one here, so we've got plus 2 outside the function, so that would look like that. And we notice that our normal intersection point of 0, 1 has moved up to 0, 3 because we are adding 2 onto all the coordinates. That makes sense. And then what we do need to be careful of here is that we can see that it's coming down and it's clearly getting infinitely closer to a particular value, but it's not the x-axis anymore. The asymptote, because the asymptote is a y value, it's y equals 0 all the way along, it is being affected by this transformation and it is being moved up by a unit, so in this case by 2 units. So we do need to draw on our asymptote. So just grab this. Now really you would do this with a dashed line in the exam so it's distinct from your x-axis. Going to pop that in like that. Okay, and always remember to label. So sorry, it's still on the line function there. There we go. So yeah, horizontal asymptote is going to be a y equals asymptote. Be careful with that. I know it's tempting to call it an x equals because it's on the same, it's like parallel to the x-axis, but have a look what it cuts through. It cuts on the y-axis. So y equals 2. You really would need to label that in the exam. That is going to be worth a mark when they're asking you to do sketches of these transformed exponential functions. So there we go, line there for the asymptote. We need to do the same for the green. So the green is 2 to the x minus 1, so that's going to look like an f of x minus 1. Everything shifted down. Intersection point is now 0, 0, because we've taken 1 away from that y coordinate. And our asymptote is going to move by the same amount, so it's going to go down to -1 as well. So we'll just draw the line in here. There we go. And then here we go, and label it. So y equals -1. 1. Lovely. Okay, now we've got a couple more to do. We've got the same thing but inside the function now. So this is another translation. And it's going to be by the vector. Now 0 on the y's because it's inside the function, so it's x values only. And then because it's inside the function, it does the opposite to what we'd expect. So it's negative a at the top there. So if it's plus 2, for example, we would move 2 units to the left. So having a look at the example, in fact that's the example I've got here, f of x plus 2, 2 units to the left. So again, you'll notice of all these transformations, the shape of the graphs are very, very similar. So looking at the exponential shape of the red graph here, the blue one's very similar. It's a bit steeper, it cuts higher up. Now to work out this value, we would need to make sure we take our function and put in the value of x equals 0. So we'll just do that now so we can check. There we go, we get 0 plus 2, 2 squared, which is 4. Obviously on this Desmos graph it's already labelled, but when you do your sketch you'll need to make sure you really do get the correct intersection point to label. And we're looking down as well to see if the asymptote's been affected. So it looks like it's taking much longer to get down close to the asymptote than the other two graphs, but it is still y equals 0, and that's because for these set of functions the asymptote is related to y values, not x values. So any transformations in x values will not affect your asymptote, so we do not need to change that here. We just need to take note of the new intersection point the graph passes through. So here's another example here, x minus 1, shifting everything to the right. You can see the green graph's moved over more, and it has a new intersection point, so 0, and we'll work it out quickly. So y equals 2 to the 0 minus 1, so it's 2 to the negative 1, which is just a half. So here we've got 0, a half as our intersection point. Same asymptotes. Okay, good. I think we've got one more transformation to have a look at. Doing very well. And okay, so it's 2 in 1 here. So it's the timesing by negative 1 both inside and outside the function transformations. Now we need to remember that both of these are reflections, and then the bit that everyone often gets the wrong way around is which one's which. So negative inside the function means your x values are affected. So just remember that's really what it means. So all of your positive x coordinates become negative and all your negative x coordinates become positive. And if you just imagine that kind of movement from negative to positive on the x-axis, then you will see it is a reflection in the y-axis. So it's kind of basically the opposite. And then y equals minus f of x. Again, this is affecting your y values. So positive y values become negative, negative become positive. This kind of up and down reflection. So it's a reflection in the x-axis. So you can see here, red graph is y equals 2 to the x. Blue graph is y equals minus 2 to the x. So that's the f of minus x there. You can see it's a reflection in the y-axis. And you'll also notice, hopefully, that this blue graph looks exactly the same as the y equals half to the x that we had earlier. So negative inside the function here has the same effect as reciprocating the base. Yeah, it's exactly the same function, just written in two different ways there. And then you've got the green one, which is negative outside. Note how I put brackets here. You need to be very careful of writing something like that, just in case someone misreads it as meaning minus 2 to the power of x, which is not what we're dealing with here. We are dealing with working out 2 to the x and then negating the answer. So we get this flip in the x-axis down here, this green one. Yeah, you just need to remember which way around these two transformations go. It's always worth, if you feel like you're going to do a bit of a 50-50 guess in the exam, it's always worth just taking an example, thinking of some numbers, really getting it right rather than missing out on those relatively easy marks that you'll get from that. Okay, final section that I wanted to look at in this video, and that is basically meeting the wonderful y equals e to the x. So let me just open this up a second. Okay, so y equals e to the x. Now you've either met this E before, or you've got no idea why we've suddenly got a letter that isn't A in there. And the way that I want to introduce this to you is to have a look at some of the y equals a to the x graphs, which you can see I've got 4 of them here in red. And then on the graphs with them, I also have in blue these graphs here. Now, to be fair, there's quite a lot of content behind this that you won't have learnt yet, and I'm not going to try and go through all of that for the sake of explaining this. But basically, this function here is what you get when you do the derivative, so when you differentiate the red graph, so y equals 2 to the x. Okay, so you will have done differentiation. You'll know what it means to work out the gradient of a curve. And what this blue curve therefore is every y value on this blue curve will be the gradient of the red graph at that particular x coordinate. And it just so happens with exponential graphs that when you do the gradient function, you just get a constant times the original function. So here it's 0.693. And for those of you that have learned a bit more and you're just coming back to revise, this is actually the value of ln 2, ln being log base e, which we will explain in some of the other videos in this series. So that's what that number, it comes from differentiating 2 to the x. So just look at all 4 graphs together. So all I've done is I've just slightly increased the base number each time. So 2.5 to the x, and then we get a slightly different number come out when we differentiate. And then we've gone up to 3, and then 3.5, and then I've reworked out each time the new gradient function and plotted it on in blue. Now what I want you to notice here when we're looking at this is how the red and the blue graphs are related to each other. So here they have the same shape, so clearly when you differentiate an exponential function you get an exponential function back, which is very exciting. It's not something that happens for many functions at all. So here the gradient function sits just below the original function. And then if we increase the base slightly to 2.5, we can see that obviously the red graph itself gets slightly steeper, but also that its gradient function, the blue graph, gets suddenly very much closer to the red graph. Okay, the gap has shrunk quite a bit just by increasing the base to 0.5. And then when we go up to 3, something even more interesting happens, and we went from having the original function, the red graph, was above the blue graph, to now the blue graph is above the red graph. And you can see it's because this constant that comes out when we differentiate went from being just under 1, so 0.916 lots of the old graph, to just over 1. And obviously if you times by something that's greater than 1, you get larger. So that's why our blue graph is slightly higher than the red graph. And then you can see if we carry on going higher, now the blue graph seems to be getting further away from the red graph. And you can imagine if we carried on, it would just get, the gap between the red and the blue would get more and more. So what I want us to take from this is that between this graph and this graph, there must be a base value, a number that goes in there, a base number between 2.5 and 3, for which the blue and the red graphs, the lines, are exactly on top of each other. If we can start underneath it and get closer and then go past it and get further away, there must be a value in between them. And that's what this E number is all about. So we're going to get rid of those for a moment and show you. Here we go. So I've 2.72, so that's in between 2.5 and 3. Put that into Desmos, and this is what happened. You can just about see there's a bit of a redness underneath this blue line. That is because they are right on top of each other. And this number that comes out when you do the gradient, that is very, very close to 1. I know it looks like 1 there, and I put ... and that's because I haven't taken the exact value of E, I've just taken a rounded value. Therefore there are actually some decimal places lower down here, but it's close enough to 1, certainly for the graph to be very convincing that the function and its gradient are one and the same thing. So we are meeting this E number then. E equals, now it's 2.72 there. I'm just going to write out a couple more digits so you can see what it's like. 2.71828, etc. This number is very much like pi. It's irrational. Its decimals go on forever with no particular pattern. It is one of the 5 most fundamental constants in maths, along with 0, 1, pi, e, and then the other one is I, which most of you probably haven't heard of, but basically it's the square root of -1. And if you do the further maths A level, you will learn all about that and how it works. It's an imaginary number. But anyway, point being is it has its place there in some very important numbers in the world of maths. And this is why. It is because it is the function that brings itself back, exactly itself, when you differentiate it. So I'm just going to bring up the little formula box here. This is the bit we've just covered. Sorry. Yeah. Here. There we go. So when y equals e to the x, dy by dx equals e to the x. Okay, absolutely no change when you differentiate. That makes exponential functions very nice to differentiate, as you can imagine. There's no bringing the power down, taking one from the power, and then there's also a lot of other differentiation techniques that you will learn in year 2. And this is just one of the nice ones, differentiates to itself. So just picture the graph. Okay, that's all you need to do. Now, there's an extra bit that we need to learn here. The only other bit of differentiation that you'll do in year 1, and it kind of frustrates me a bit because you're kind of expected to just learn this and use it. You don't really know why until you get to year 2 and you learn something called the chain rule, which I will mention now just to give you some idea of where it came from. The general idea of the chain rule is that when you're dealing with a function within a function, so you might have called these composite functions in the past, you differentiate what I call the outside function, and then you multiply by the differential of the inside function. And applied to this kind of scenario, it would be if you had some kind of function sitting inside an exponential. So the exponential function is a function itself, and then there's something else going on inside there. If I was to differentiate this, so d by dx of e to the f of x, I would get e to the f of x back, and that's because e to the x differentiates to e to the x. So that is me differentiating the exponential. It doesn't do anything, so I get the same thing back. And then I would multiply by the derivative of what's inside, which we would call f dash of x. So if it was e to the x squared, I would get e to the x squared times 2x, because that would be the differential of the x squared. Now you don't need to know it to that level for year 1. You just simply need to know that if there is a linear term, so by linear term I just mean a number times x in the power of e, so e to the kx here, they use k as the example of the constant, then when you differentiate you get k e to the kx. And that k is there because the differential, if you differentiate kx, you just get k. So if you differentiate 3x, you get 3. If you differentiate 10x, you get 10. So that's that number there, that k, is coming from timesing by the derivative. You need to be very careful, seeing as this is the only other bit of differentiation that you learn in year 1, that you don't mix it up with the polynomial differentiation. So that's when you've got a function like this, and you differentiate it and you get a n x to the n minus 1. So that's the bulk of the differentiation that you do in year 1. That's what you kind of get used to. So what you then need to not do is see something like this and go, oh yeah, no, that's fine. I can just bring down the power and take one from the power. So it will either come out looking something like that, or it might come out looking something like that. Okay, so nope, do not do it. Think carefully. Recognize straight away that you are dealing with a very special function, an e to the x, and just follow this formula, or even better, learn the chain rule, and then you'll actually know what you are doing. I mean, you're not going to be doing the exam until you've done the whole of year 2 anyway, so you will have learned the chain rule. You'll understand it a lot better then. But those of you that are just doing the AS, you won't venture as far as the chain rule. So this is why. Okay, we're multiplying by the derivative of the function that sits inside the function that we have just derived. Do not get them confused. Okay, so that brings us to the end of what we're going to cover in this video. In the next video, we're going to have a look at a whole bunch of examples that cover the graph transformations, sketching, e to the x, questions about graphs that don't require any sketching. So we're going to try and cover all the different types of questions that you could get. I'm going to be working through them, so you can work through them with me. Good bit of revision for you. And then the graphs following that in the series will cover, the videos following that one in the rest of the series will be looking at the rest of the content for exponentials and logs. So we'll be looking at the log laws and solving exponential and log equations, and then eventually modelling and looking at linear graphs with logs. So thank you for watching. Hopefully you found it helpful. If you did find it helpful, then please hit the like button, and don't forget to subscribe if you'd like to see more videos like this on both the A-level and also covering the GCSE content as well. And I'll see you in the next one. Bye.